Jai Hind all, myself Amita Asthana from AKGEC Ghaziabad. Here in this video lecture, we will discuss the topic analog to digital converter. The topic is being taken from the 5th unit of the digital system design case 302. So here the analog to digital conversion process, we must understand how the analog data is being converted to the digital data. So basically there are three steps. First is the analog input is being sampled and then it is being sampled using hold circuit, and then the hold values or sample values are being quantized, and these quantized values are then encoded, and hence we can get the analog to digital converted output. So basically three steps are involved. First is sampling, second one is quantizing, and the third one is encoding. So here is the block diagram in which we can see the analog signal, and analog signal is being sampled using the sampling and hold circuit, and these are the sampled values, and these sampled values are divided into the quantization levels, and according to the levels, wherever the sample value falls, that level is being already encoded, and that sampled value is given that encoded value. So the analog data is being converted to the digital data in this way. Here, sampling and hold. What is the sampling and hold process? Suppose we are having a continuous signal in this way, and the continuous signal like this, we have sampled all the values. The time interval taken between the samples is delta t. So all the values at the delta t interval are being taken, and these are the sample values. Now all the sample values, all these sample values are the discrete states of the digital system, and these sampled values are being held by the circuit. Let us see the circuit. So before going to the sample and hold circuit diagram, we must understand the time during which the samples are being taken, that is known as sampling time. Okay, let us let's say we are sampling at the delta t time interval, so the sampling time will be delta t. So how that we should put a limit on delta t? What should be the value of delta t, that we will see. So the duration of the circuit for which the sample value is being held. So for the time duration delta t, this sample value should be holded, and this is known as the holding time. So there is a sampling time, the time during which the sample and hold circuit generates the sample, that is known as sampling time, and the time duration in which the circuit holds the sampled value is known as holding time. So the sampling time, generally it is taken between 1 microsecond to 14 microseconds, while the holding time can assume any value as required for the application purpose. So there is a special component which is being used for the sample and hold circuit, that is nothing but a simple capacitor. So here capacitor is the heart of the sample and hold circuit. The capacitor charges to its peak value and holds that value until it gets discharged. So the discharging will be taken place whenever the switch is being closed. So let us see this circuit. So here the Vin value is being given, the sample and hold circuit, the block diagram is being shown, and the output we will get in the digital form. So the command will be given to this sample and hold circuit like this: sample hold, sample hold. So there are two basically main processes while ADC conversion, that is sample and hold, sample and hold, sample and hold, like that. Now the circuit diagram, suppose we are giving the analog input AI in this way, This is the control signal which we are giving. This is the circuit, and this circuit is being switched off and switched on according to the control signal. Now, if this circuit is, let's say this is switched on, then the capacitor will be charged by that value. And now the requirement is their capacitor should not discharge. So the capacitor, whatever the capacitor, the holding time of capacitor should be maintained so that it can carry that whole that sampled value for the given time interval, and then by the using the amplifier we can get the analog output. So this is a basic sample and hold circuit diagram for the ADC. Here we can also use the practical circuit. So in the practical circuit of sample and hold circuit, we are using n-channel enhancement type Mosfet, one holding capacitor as before. So this is a kind of, you can understand like a switch. So this is the holding capacitor which we are using, and this is the operational amplifier. So there are three main blocks, 1, 2 and 3. So this is the amplification, this is the holding circuit, and this is kind of switch. So the n-channel E Mosfet. Now let us understand how it works. The n-channel enhancement Mosfet is using as a switching element. So input voltage is applied through its drain terminal. Here we can see the input voltage is being applied via the drain channel, and then control voltage to its gate. So here we are giving the control input voltage to its gate, and accordingly whenever the positive pulse of the control voltage is applied, the Mosfet will be switched on. Okay, for VGS to be greater than 0, the n-channel Mosfet should be on, and it is acting as a closed switch, that we already know. Whenever the control voltage becomes 0 or less than 0 values, the Mosfet gets off and it acts as open switch. So the switching of the Mosfet on and off can be controlled by the VGS voltage that already we have studied in the last semesters. The capacitor charges. Whenever the switch is on, the capacitor charges to its peak value, and when the Mosfet switch is open, the capacitor stops charging, and for that time the capacitor holds that value. Due to the high impedance operational amplifier connected at the end of the circuit, the capacitor experiences high impedance. Due to this, it cannot get discharged. Okay, so charge is held by the capacitor for a definite amount of time, and that particular time, the capacitor holds that charged value is depending on the holding time of the capacitor. So that is known as holding period, and time in which samples of the input voltage is being generated, it is known as sampling period. So in this way, the Mosfet switching on, switching off, switching on, switching off, and the capacitor is charged, hold, then discharged, hold, like this. So this is the complete process. Now analog to digital conversion, next steps are quantizing and encoding. So quantizing is all the sampled value are being level assigned, and these levels are encoded already, and then each state for input to the each state wherever the sample value falls, that takes that encoded value according to the sample value. Now the analog quantization size which we are taking, that is Q is V maximum minus V minimum upon 2 raised to the power n. That means if we have n quantized level, okay, so if the sample value falls here, okay, then if this is the mid value, if this sample value is above, it will take this level, and if this sample value is below this midpoint, it will take this value. It is, let's say it is encoded in this one, and this is encoded in like this. If it falls, then the encoded value will be like this, and if it takes this level, then it will be encoded like this. So this is how we are encoding the quantized signal. So here it is the better representation. We are having all the levels, the sample values are falling, and according to the levels we are giving the the encoded or encoding of that sampled values. Now, so there are error possibilities also for analog to digital conversion, that is aliasing. And aliasing, whenever we are not following the Nyquist rate criteria, aliasing error can produce. And for removing the aliasing, we must assure that the sampled frequency must be greater than the twice of the maximum frequency component present in the signal. So Fs should be greater than equal to twice of Fm. This rule must be followed for removing the aliasing error and then quantization error. So if the resolution is better, then we can remove the quantization error, and this is basically depending on the microcontroller. Now coming to the types of ADC, so we need to study three types of ADC in this unit. That is, first is successive approximation converter, and then flash type, and then dual slope. And all these three types are very important for the analog to digital conversion. So here coming to the first type, successive approximation ADC. So let us understand this one. This is successive approximation register, SAR. This is the digital analog conversion. Some clock input is being given to the SAR, and this is end of conversion, EOC. This is some sort of reference voltage we are giving, and one comparator is being used, and this is the Vin value which is to be converted into the digital data. Now let us see all the terms: DAC, digital to analog converter; EOC, end of conversion; SAR, successive approximation register, and this is sample and hold circuit. This is the input voltage comparator and the V reference. So all the blocks are included in this block diagram. Now understanding this one by one. So what should be the first step? So here this is the input voltage which we are giving. This goes to the comparator. Now initially what we do is all the values here are set at, in the successive approximation resistance, all the values or bits are stored at the 0 level. Only MSB is kept at the 1, that means at the higher value. So the first step is, this is using n-bit DAC and original analog resistance. MSB is initialized at 1 for DAC. Okay, right? So what it does, see here. So MSB is initialized at 1, others are at 0. Now some reference is being given. Digital to analog conversion according to this one takes. These are being compared, and if it is greater or if it is less, then the comparator output will be either high or low, right? So it will be giving some V in or the value according to this one. Whenever these two are equal, then the end of conversion will take place. This is the concept for this successive approximation ADC. So here let's say Vin is less than VDAC, reference which we have already given, and MSB is reset to 0. Okay. So Vin is greater than DAC, successive bit is set to 1. Algorithm is repeated up to LSB. All the LSB are being, that means as if the value is less than that, the bit will be set to 1 whenever this Vin is less than VDAC. Whenever Vin is greater than VDAC, then successive bit is set to 1. So what it means is, whenever Vin is greater than the DAC, see what is happening here. We are getting some VDAC. If this value is greater, we will increase the bit here. Okay. If this is less than, then we will decrease the bit here, so that again the data can be compared. So this will end up to the LSP, right? So at a point there will be a stoppage whenever this D1, D2 and all the bits are equivalent to this V in, then the end of conversion will be there. Okay. So at the end, DAC in will be equal to ADC out, and n bit conversion requires n comparison cycle. Let us take an example to understand it well. So what we give, suppose we take a 5-bit ADC, right? Now cycle 1, MSB is set to 1, the SAR register is set to 1000. As I told, the MSB is set to 1. Okay. Okay. So V DAC will be V reference upon 2, that will be 0.5, right? Now this is again found that V in is greater than V DAC. Then what we will do? We will put this, convert this 0 to 1. So the value will be 0.75. Now 0.75 will be compared to V in. Again, this is found that V in is less than V DAC. So in cycle 3, what we will do? We will make it 0 and we will increase this one. Okay. Because it is clear that if we put 1 here, the value will be, this V DAC is greater. So we will reduce this V DAC. Similarly, all the cycles will be repeated and to get the final output. And voltages will be converted, and final SAR, whatever the successive approximation register will contain, that will be the final value of the input voltage. Now coming to the flash ADC, it is a simple analog to digital type of converter where we are giving octal input, all the comparators are being there. Encoder is there that converts the output of comparators to binary, and following the simple rule that V out is compared within the V1 and V2. If V out is equal to Vs plus, when V1 is greater than V2, V out is V1 is less than V2, and accordingly the octal input can be converted to its binary data. Now coming to the flash ADC. So here, where let's say if we take the 8-bit, then we need to take some op-amps, and these op-amps are according to the bit which we are going to take. Like here we are using one priority encoder circuit, as you can see, the priority encoder, and here we are using number of op-amps, W1, W3, W4, W5, W6, W7, right? Whatever analog input we are giving, so this will be either plus VSAT or minus VSAT, and here these will be at 1100 like this. Let's say the flash ADC output is depending on the resolution. The resolution delta V is equal to V reference upon 2 raised to the power n, where n is the encoder output bits. So how many comparators we are using? That will be 2 raised to the power n minus 1. For 3-bit, let's say, so we will be using 7 comparator circuit and 1 priority encoder. All the op-amps output will be given to the priority encoder, and 1 additional encoder bit we can use, that is 2 into comparator. So not to confuse by this, just only we need to for 3-bit we will calculate the number of comparators, 2 raised to the power 3 minus 1, and then all the input will be given simply to the priority encoder, and according to the priority encoder functioning, we are getting the MSBs and LSB from Y0 to Y2. Okay, so flash ADC example we take, just let's say we are giving some voltage V in as 5.5 volt. The V reference is 8 volt. So V in, to looking at this value is lying between 5 and 6. Okay, so let us look at the comparator number 5 and 6. So the value, analog value which we are giving, that should lie between these 5 and 6 op-amp outputs or comparator outputs. So V5 comparator will be V reference 5 by 8 and V comparator 6 will be V reference 6 by 8, that is 6 volt. Now comparator 1 to 5 will be set at 1 and comparator 6 to 7 will be set at 0. So the encoder octal input will be some 0 0 1 1 1, all the bits at 1, 5 ones and 2 zeros, and encoder binary output accordingly will be equal to 101. So here again we are having dual slope analog to digital converter. So this is a integrating type of ADC. Here we are using one op-amp. The input voltage and the reference voltages are being given and the comparator output is controlled by this particular circuit, and the dual slope ADC, how it works. The unknown voltage, let us applying to the input of the integrator and allow the ramp for the fixed time period TL. So here we are giving this V in and this is the TL time for which the allowed to ramp for a fixed time period TL, TU. A known reference voltage of opposite polarity is applied to the integrator and is allowed to ramp until the integrator output returns to 0. So V in will be equal to minus V reference TD upon TU. Okay. So here one integrator and one ramp. See, this is the integrator and this is the comparator. So here we are using the input voltage is applied to the integrator circuit and then it is going to be compared with the control logic. Okay. So the input voltage is computed as a function of the reference voltage and the constant run-up time period and the major rundown time period. So the rundown time measurement can be controlled by the converter's clock circuit here, the control logic and the counter. So whenever the clock will start, there is a counter and this counter will give the value analog according to the control logic, and hence the counter, whatever the count represented by the counter, that will be the corresponding digital output for the given analog input, and hence the circuit is being used for converting analog to digital conversion. So the comparison of ADCs, as we can see, the dual slope flash and successive approximation, the speed is relatively, very fast in flash type, successive approximation medium, and dual slope is really not so much being used, and hence the resolution is being compared and the cost is being compared as represented in the slide. Thank you.